Hi Logic fans, what's up? It's Ash again, and today we're going to cover section 6.8, our 8th section on quantificational syntax. Here we're going to look at theorems, and theorems we'll see correspond to the exact same thing as theorems for propositional logic in chapter 3. We're also going to look at definitions of some central quantificational concepts like logical equivalence, for example, and some others. Alright, let's rock. Okay, so before we can really get into proving theorems, which is what we really want to do syntactically, we should just note a few things that we take for granted at this point, okay? So we're going to take for granted that you understand universal instantiation, universal generalization, existential instantiation, existential generalization, quantifier negation, conditional proof, and indirect proof. All of these come into play, and you really have to have all of them down in order to be in the process of proving and really digging into quantificational semantics. So if you're unfamiliar with these or you're otherwise a little shaky on them, make sure you go back to the previous videos and really get those down before moving on here. Okay, so the first thing we need here in order to start talking about theorems are to remind ourselves of some definitions. So the first one here is just review, okay? A quantificational deduction, much like a propositional deduction, okay, is an m by 2 grid. So here's an 8 by 2 grid, okay? Where every quadrant in the leftmost column, that would be this one, contains exactly one quantificational sentence. And notice that's true. I've put some spaces in here just for readability. Contains exactly one quantificational sentence, and every quadrant in the rightmost column indicates whether the sentence to its left is a premise, an axiom, or follows from one or more previous sentences by syntactic rule. So we don't have any axioms in this case, but this indicates that this sentence is a premise. This indicates that this sentence is a premise. Okay, and this is just an example of what a quantificational deduction is by definition. Okay. Now a quantificational proof is a quantificational deduction with no premises. Okay, so this is not a quantificational proof because it has premises. Okay, so we're going to see plenty of examples of quantificational proofs today because we're going to be proving theorems, right? A theorem is any quantificational sentence which is the last line of at least one quantificational proof, one of these guys. So it's a quantificational deduction without any premises, and whenever you can get that, whenever you can prove a sentence from first principles alone without the benefit of any premises or any extra logical equipment or assumptions, then you've proven a theorem of logic. You've proven that a given sentence is a theorem of logic. So with those definitions in mind, let's go ahead and look at some examples. Okay, so we indicate that a given sentence, like this one, for example, is a theorem of logic, right? It can be proven. It's a syntactical, you can syntactically deduce it without the benefit of any premises or any extra logical assumptions. We indicate that a sentence like this one is a theorem with this turnstile. So this means it is a theorem of logic that for all x, either x has the property f, or it's not the case that x has the property f. So, for example, pick anything you like out of Santa's bag. Whatever you picked out, it's guaranteed to either have the property f, or it will not have the property f, okay? And this should remind you of a certain axiom. And since we're going to prove that this sentence is a theorem, right, without the benefit of any premises, we must start with either an axiom or an axiom or an assumption. Okay, so those are your two options. We do not have the benefit of premises. So basically then what we want to do is we want to figure out what we should start with. Should we start with an axiom or should we start with an assumption? If we start with an axiom, which axiom should we use and what should it look like? If we start with an assumption, what should it look like? Okay, what assumption should we make? And this problem can be done either way. You can do it with an axiom or with an assumption, but let's just start with the basic idea of how do you figure out how to start, right? How do you figure out what your starting assumption or what your starting axiom should look like? And the big key here is to use reverse engineering. Okay, so just like in chapter 3, we're going to reverse engineer this guy. So let's start it like this, okay? Let's suppose, so this is just scratch work, this is not our official proof. Let's just suppose, for the sake of argument, that you had this sentence, okay? Who knows how you got it, but you got it one way or another. The question is okay, supposing that I had it, right? Can I use the rules that I have to manipulate this thing into a recognizable assumption or into a recognizable axiom, okay? So supposing that we had it, pause now and see if you kind of can reverse engineer this thing until you find either an axiom or an assumption. Pause now. Okay, and we're starting easy, but that's the idea, right? If I had this thing, I would universally instantiate it, and I would end up with FU or not FU. And I already recognize an axiom, so I am ready now to go ahead and do my actual proof. So what we're going to do here now, having discovered that I'm going to be using an axiom, okay, and which one it is, we're going to write up our official proof. So we're going to have our lines and our rationales, and not a single one of these is going to be a premise. So pause now and see if you can figure this one out. Okay, and the reverse engineering technique yields results, right? I mean, here you've got just a two-line proof, and you don't even need your scratch work anymore. Your official proof would look just like this, okay? And so you've got, it's a theorem of logic that for any x, either it has f or it lacks f. And here's your proof, right? From first principles, no premises. And the sentence in question is the last line of a quantificational proof, which is a deduction without any premises. So by definition, this is a proof that this is in fact a theorem. Okay, let's try some more. Okay, let's prove that this familiar looking, this should remind you of a theorem from propositional logic, in much way the last one did as well. What I want you to do here is I want you to start, we're going to prove that this sentence is a theorem, and indeed it is. I want you to go ahead and prove it, but to start that, let's do some reverse engineering. Suppose you had this, right? So this is just our scratch work. We're going to figure out how to start. We need either an axiom or an assumption to start with. So supposing you had this guy, right, available, what could you do to it and sort of strip it of its quantifier and break it down to a point that you see either an assumption you could make or an axiom you could invoke? Pause now. Okay, and again, the reverse engineering process here is very simple. Other ones will be more complex as we build up in complexity. But yeah, if we had this thing to start with and we would just universally instantiated it, we would end up with this expression. Well, this has the main connective here, and so this is a conditional, and therefore conditional proof is recommended, where this is the antecedent, and this is, so in other words, this is what's assumed, and this is what we look for. So on that strategy, go ahead and see if you can't go ahead and prove that this is indeed a theorem of logic. Pause now. Okay, and hopefully you were able to get it. So we assumed the antecedent, FU or FU, and from that we needed to get FU, the consequent, and that was easy to get using the rule idempotence. And so having obtained what we wanted from the assumption, we discharged it, and we ended up with the thing we assumed, arrow, the last thing we got, which is FU, and then it was just a matter of universally generalizing back, and it wants it in terms of x as opposed to y or z, so we universally generalized to x. All right, let me make this final observation about this problem, just sort of as a general problem-solving technique that you can invoke. So here you have, if you had recognized sort of the theorem idempotence, right, in propositional logic, right, we had this theorem, and we proved that in chapter 3. And notice that the proofs are very, very similar. And so one thing you can do when you're looking at a quantificational sentence is you can try to imagine in your mind's eye a propositional analog of it. And, if you reverse engineer this, you're going to get basically the same procedure that we got when we reverse engineered this. And, if you can prove the propositional analog, this way, that can give you a very strong hint and clue as to how to go ahead and prove the quantificational sentence, which is a bit more complex, but sort of keeping in mind this idea of looking for a propositional analogy or analog of a quantificational sentence can often give you an insight into how to solve problems. So keep that in your back pocket and sort of in your mind's eye as a possible problem-solving technique to help you along. And all right, good. So let's look at another problem. All right, so let's build up in complexity a little bit, consider a different kind of case. These are going to get a little bit harder as we go, but building in confidence. This is a theorem of logic. Pay very close attention to what kind of sentence it is. What's its main connective, for example? Okay, is this a universally quantified sentence? Is it a disjunction? Is it something else? Pay close attention to that, and you're going to prove that this is a theorem. And again, you don't have the benefit of a premise. You have nothing to start with, so you've got to figure out something to start with. In order to figure out what to start with, we're going to reverse engineer it. So can you look at this thing and figure out maybe what you should start with? Pause now and just see if you can do that. Just figure out what your starting routine might be. Pause now. All right, so in this particular case, this sentence here that's a theorem of logic is a conditional, okay? And notice the classical assumption that we're working with a non-empty domain plays a critical role here. But this says if everything has, on the condition that everything in the universe is F, something in the universe is F, okay? So it's a conditional whose antecedent is a universally quantified sentence and whose consequent is an existentially quantified sentence. So supposing we had this, you would just sort of assume this, right? That would be your assumption, and you would look for this existentially quantified thing. And note, if you couldn't quite get that, you could assume its negation for nesting an IP assumption if you wanted to, but we're not going to need that. So with that hint, see if you can't go ahead and write up the actual proof that this sentence is indeed a theorem of logic. Pause now. Okay, and hopefully you were able to get it, but yeah, we just sort of made our assumption, right, which was everything is F, and from that assumption we had to show that at least one thing was F. So we universally instantiated, then we existentially generalized, and having obtained what we wanted from our assumption, we discharged it, and we ended up with this in the antecedent, and this is the consequent as desired, and so that is our official proof that this sentence is a theorem of logic. Good work. Okay, because of the time constraints, I want to move us into the next video where we will continue this discussion and define some important syntactic concepts. So be sure to catch the next and second video on section 6.8, Theorems 1 and Central Syntactic Concepts.